Hi, I'm Nancy Friedrich, editor of Microwaves and RF, here at Anritsu with Bob Buxton. Hi, Bob. How are you doing today?
Nice to meet you, Nancy.
I'm looking at Anritsu's newest synthesizer, which is quite an impressive unveiling from them this year, as usual. Bob, tell me a little bit about the synthesizer. Its standout features seem to be its low phase noise and wide frequency range, correct?
Yes, that's exactly it. The whole range extends from 0.1 hertz all the way up to 70 gigahertz. We have models in between that stop at lower frequencies like 10, 20, 40 and 50, but the real standout feature for coverage is 0.1 to 70 gigahertz. That really gives engineers the capability to generate baseband signals, IF signals, microwave and millimeter wave signals, so they can test essentially all parts of their design with one box. Mm-hmm. You mentioned the phase noise as being another standout feature, and that's perfectly true as well. Critical for people who are designing radars and people who are designing digital communication systems.
Why is it important for the people designing radar in particular?
Well, for radar in particular, it all comes down to how phase noise affects the radar signal. If I might just show you.
Okay.
What we're looking at here is essentially a transmitted signal from a radar shown in the frequency domain. So we're looking at carrier and phase noise. It goes off and hits a target, comes right back. That target's moving relative to the radar. It has Doppler shift. Different Doppler shifts happen at different velocities. So it could be ranging from a few kilohertz to a few tens or even hundreds of kilohertz. So the sweet spot for radar designers is right there, and that's where we've really focused on bringing down a lot of phase noise.
Okay.
Also, for some of the lower frequency comm systems, we focused close to carrier as well, and lower bitrate comm systems, we brought down phase noise there.
Okay, excellent. Are there any other features that are relevant to radar designers?
Yes, exactly. Great question, Nancy, because in addition to the whole concept of having low phase noise, it's very critical to generate the right type of pulses to simulate radar returns and do that in a controlled way. So one of the big features that we have in this product is the ability to level pulses, amplitude level pulses, down to pulse widths as narrow as 100 nanoseconds. And I can show you that here. What we have is a pulse demonstrated here on the screen, and even if I change frequency, that pulse amplitude stays the same. It doesn't transition to a CW signal, which if it did, that would cause damage to the radar receiver. Secondly, we have the unique ability in the 3690C series to actually generate multiple pulses to simulate multiple radar returns. So the way we do that is we can generate either single pulses, which we're showing here, or double pulses, so now simulating two targets, or triplet pulses, simulating three targets, and with different delays, independently programmable. And then finally, quadruplet pulses. And we can control the delays and the pulse widths independently. Very useful for radar designers.
I was interested also in your the fact that you target baseband designers. I've noticed that it's become a trend to have a solution that helps test the baseband as well, because that was often kept separate from the RF. So can you tell me a little bit about the benefits of that in the design cycle?
Well, I think the critical thing there is you have to look at the system as a whole.
Okay.
And you're looking at everything from the signal processing all the way up to through the baseband processing, through the IF generation, through the up conversion chain to transmit frequencies, and then back down through the receiver. So again, having one box that can go all the way from baseband signals to millimeter wave frequencies means the engineer's got one box on the bench, less clutter.
Right. Okay, excellent. Did you want to show us an example that would be more apt for communication systems designers?
Yeah, for comm systems, what we have here is, when you're looking at a digital comm system, it's all about the IQ diagram and error vector magnitudes. So if you've got a simple scheme like QPSK, phase noise, which translates to error vector magnitude, isn't so critical because you don't confuse symbols, they're all distinct. But when you go to a higher order modulation scheme, so you can cram a higher data rate into a narrow bandwidth, the same level of phase noise will cause bit errors.
Okay.
And when you then get a system that has low phase noise, now you can distinguish between all those different symbols. The 3690 series of signal generators has 0.1% error vector magnitude for a 10 gigahertz signal. And engineers are normally looking at error vector magnitude of 2%. So essentially the generator is invisible as part of the test. It doesn't influence the test results.
Excellent. Very impressive. Well, I hope that you garner a lot of attention with this product, and we wish you a lot of luck. Thanks so much for telling us about it.
Thank you very much, Nancy.